Welcome to the presentation about GPGPU as a service and especially about the GVirtuS experience. I'm Raffaele Montella from the University of Naples Partenope, Italy, Department of Science and Technologies. First of all, why GPGPU as a service? Well, we have to consider two scenarios. The first one on clouds. Big cloud computing vendors already offer GPU-enabled virtual machine instances. The most part of them offer this kind of instances using the pass-through approach. That means it's not actually multiplexing and remoting GPUs, but assigning GPUs actual resources to virtual machine instances. This is very high performance, but is also costly because usually GPUs are a scarce resource. It's a very good solution for demanding computational loads to be executed one shot on clouds, but and these enable the allocation of computing resources in a better way, even the rent of GPUs, but this is still not multiplexing. While GPU as a service has in the vision of what is presented here could be interesting for on-clouds deployment, because it enables allocating computing resources in a better way, even renting multiplexed GPU's resources, and improve the business in the case of public clouds. And of course, if I can offer GPU resources in a cheaper way, this could be more interesting for my customers because they can save money on the cloud bill. And of course, as a cloud vendor, I can extend my business. But maybe the most interesting scenario is on premises and on private clouds, because in this way the main focus is optimize the computing infrastructure procurement. Really often, especially in public administration, the procurement in high performance computing and in private cloud infrastructure could be an issue because the huge amount of money involved, and in this way, using virtualized and multiplexed GPUs is possible to optimize the procurement and even to minimize the total cost of ownership. Basically, the target is enable machines that could be virtual machines or physical machines that are not provided by GPGPUs to execute GPUs kernels. GPGPU's kernels, usually we consider the multiplexing of computational resources carried out by GPUs, not for visualization. Examples: minimize the teaching cost in classes involving on the teaching of GPU programming, but even the teaching of GPU leveraging applications as machine learning, for example, and even in the case of business and startups, minimize the time to market for having a more flexible infrastructure. This is the typical schema of GPGPU as a service. So we have physical machines or virtual machines. Physical machines are running in their environment, or virtual machines running using an hypervisor in a virtualization node, we can consider an acceleration node that is physically provided by GPU devices that can be NVIDIA or AMD. In this presentation we will mainly talk about NVIDIA CUDA, but what happens with NVIDIA CUDA happens even with other GPGPU and programming environments. Usually we consider the GPU hardware, the drivers, and the runtime that is mediated to the physical machines or virtual machines that use the multiplex of the GPUs using a backend, then a communicator component, and a front end. This is a typical pattern called split driver that is very common in virtualization and in containerization. In this presentation we show we deal about the GVirtuS experience. It works. GVirtuS is an open source software component for GPGPU virtualization and remoting. As you certainly know, it is not the only component that play exactly this role in the accelerators panorama. For example, we have the wonderful RCUDA. RCUDA is closed source, it's really high performance. It leverage mainly on communication based on InfiniBand. We can consider the GVirtuS as open source and mainly for teaching and researching purposes. We have to define the word virtualization and remoting in this field. Virtualization makes available a subset of CUDA API to virtual machines running on a host equipped with a CUDA enabled device. That means we have virtual machines that are running on a host. The host has the actual device and a subset. Usually we talk about subset of CUDA APIs that are provided to the virtual machine. Remoting is similar, but the subset of CUDA APIs are provided to a physical or a virtual machines without any kind of difference using a remote host equipped with the CUDA device. That means we have a decoupling between the physical place where the physical machines or the virtual machines are executed and the physical place where the physical GPUs are installed. We have to consider an completely independent approach for this kind of software that is to be independent by the hypervisor, by the software that mediates the virtualization, independent by the communicator, the component that enables the marshalling between the machine that uses the CUDA APIs and the machine that executes the CUDA APIs, and of course even independent GPU independent, because we are talking about CUDA, but we can talk about OpenCL and GVirtuS, for example, abstract the OpenCL and the CUDA plugins. That means we can have the same accelerator node equipped with only one or more GPUs, providing both backends plugin for CUDA and OpenCL. Basically, GVirtuS provides low power system and device with native high-end GPUs capabilities. It works with CUDA and OpenCL, and kernels are offloaded to be executed. The GVirtuS don't use some programming model. It is completely transparent because the APIs are provided by libraries that are a mocking library, a stub library to the real libraries. In this way, if an application is compiled with CUDA or OpenCL, and the support of CUDA or OpenCL, the dynamic library, can be executed in a virtualized slash remote environment by GVirtuS in a really transparent way. Actually, because the aim of a project that funded the GVirtuS, we have even a simple programming model for Android and Java. It works only for CUDA, just because the design of the project, there's no technical limitation in extending the support of the Java slash Android, or even Kotlin slash Android support to CUDA, to GPGPU support to OpenCL. This is the outline of this presentation. We will talk about the GVirtuS architecture. In particular, we will focus on the split driver model used by GVirtuS to abstract and remote, virtualize and remote GPGPU computing, and we will discuss some benchmarking. We did some benchmarking creating an ad hoc software, but even we performed some benchmark on real software because we have real problem to solve in this way. We will discuss about the Android integration, and we will show even how the GVirtuS worked on different Android device, definitely not designed to be provided by a CUDA support. And at the end we will have the usual conclusion. As I already told, the GVirtuS is open source, is definitely focused on research and teaching. This kind of application is available on GitHub. GVirtuS was for the first time designed in 2009. It was included in a project proposal called the Hope. This project was submitted to a local call for new technology project that was not found. Someone thought, okay, GPU virtualization, and in that time was even a cluster virtualization was useless. But never give up. And so in 2010 up to 2013, the GVirtuS project grew up as a research prototype. It was released in open source. During this time, the GVirtuS was in the radar of NEC, and they smelled an interesting approach of GVirtuS, and they contribute to the project, basically hiring one of the first developers. Then GVirtuS was founded by an European project, an H2020, from 2014 to 2017. It was a really good development of GVirtuS. At that time, GVirtuS was framed to CUDA 6.5 because one of the requirements was the stability, and was introduced the memory management. But the most important thing, new thing, was making it possible to offload CUDA kernels from Android device to high-end GPU devices. Finally, now GVirtuS is funded by a local project, is still under development, and basically the new interest is in use GVirtuS to offload machine learning tasks. And actually, there are some design, even there are some design topics, even for application to accelerators that are not GPUs, GPGPUs, but other kind of accelerators. as I told, the execute engine of GVirtuS is completely transparent because the libraries are fake, are basically the stub libraries. It is completely independent. It could be used by both physical machines and virtual machines. It is used by ARM and x86 machines, both 32 bits and 64 bits. The nice thing is you don't need to share the same technology on both front end and back end. You can have an ARM 64 bits mobile device offloading computing cores directly to an x86 64-bit backend, and the virtualization, and in this case remoting, is completely transparent. You're not okay. You have just to execute the CUDA command and it works. And of course, this could be done basically in any configuration because both front-end and back-end could be deployed locally in a public cloud or in a private cloud. And, any configuration of Mixabase is possible and was tested. As I told, it works on the split driver model. The split driver model is a key concept in the today cloud computing approach. Actually, the main issue is I have two sides of computation. One side is called the front-end side, is where the application runs, and the other side is called the backend, where the application have to offload part of the computation. If you are imagining, for example, in a container application for cloud computing, when you have, for example, a web server instance on the front end and an actual machine, a physical machine that have just to share libraries on the back end, basically what happens in Docker. Yes, this is exactly the right model. It works in this way. I have the application. The application invokes stub libraries. Let's say a library that perform the sum of two values. Just a typical example. The library is a system library. It should be executed by the machine where the application runs, but instead of execute a real library with a function summing two values, it is invoked another library with exactly the same signature, but instead interact with the backend using a communicator. The backend produce the actual computation, then the results are sent back to the front end. GVirtuS works exactly in the same way. The other interesting thing is where the components run. In GVirtuS, it's possible to have the front end in unprivileged domain, and it's interesting that the backend could be both in privileged domain in configuration where the main topic is share GPU computing with other virtual machines or remote machines, or even in unprivileged domain. For example, it's possible to install the GVirtuS backend on an Amazon virtual machine enabled using pass-through to use GPU devices, and then use a local machine that interact with the remote machine in order to consume GPU computing power. Basically, from the request point of view, I have the application, the wrap library, that is the stub library, the front-end driver, then the communicator, the back-end driver, the interface library, the device driver, and then finally the device. The GVirtuS backend must handle concurrent requests and have even to mediate between different threads on the same process on the remote machine, on different projects. This is easy, and it's definitely super easy to manage the connection with different backends, front ends at the same time. The point is the memory allocation, because let's say we have to allocate some memory, some part of the memory on the application, and this same memory have to be seen by the backend. The two contexts are completely different. Even because the backend could be on the same physical machine, or even on a machine on the other side of the world. This is exactly the same. Are two different memory contexts, and that means the memory addresses are completely inconsistent. Of course, it's possible using a technique called marshalling. Basically, when the some memory allocated on the host, when a function that allocates memory on the host, it is allocated on the host, and then the memory address is translated using a table on the guest side. For example, in this case, we create a new we create a new function. We push the pointer of the new function to the host. We use a way to use the name of the function in order to select the actual function that have to be executed on the host. On the host is executed the function, and then the result is sent back to the guest device. Of course, it's not possible to use directly memcopy in this case, because the memory allocated on the host could be managed on the guest side only using the function made to manage the memory. And this is an example how a CUDA function is invoked. If you are familiar with CUDA programs, the first thing that have to be done with CUDA is initialize the context, and in this case we want to get the number of a CUDA device. Of course, intentionally the code of the main program is simplified. We have to run the function of CUDA get device count. The function of a CUDA device count belongs to the CUDA SD key. The only one argument is the pointer of an integer. This integer will be filled by the SD key with the number of the device available. Now, in the CUDA lingo, in the CUDA language, we have the name host has the machine that hold the physical GPU, and we call device the device, because imagine the GPU is a coprocessor. That means it's seen as a different device on the host machine. Here in the GVirtuS we have a problem with names, because we deal with virtualization. In virtualization, we have the word guest to refer to the virtual machine or the remote machine, and host as the machine that hosts the virtual machine. In this case, we have to fill the number of GPUs passing an host pointer that actually is a guest pointer. That means we need some translation, and that means that our front end have to, first of all, get the reference to the front end. As you can see, the implementation of the CUDA get device appear to be the real one, the regular one, but it isn't. The implementation is a matter. The signature appear to be the same, but the implementation is different. We get the pointer to the front end. We have to add the host pointer is basically the parameter. Then we execute the CUDA get device count. At this point, there is the interaction with the communicator, and is invoked on the backend the function handle get handle CUDA get device count. We get back the input buffer, basically where the pointer have to be set. We execute the real get CUDA get device count. Then finally we prepare a buffer to send back to the guest device, the guest machine, the result. These are exactly the same, but with the OpenCL function. As you can see, the approach is exactly the same. It's split driver, the plugin works in the same way. It changes, of course, the signature, but even the two programming models are pretty similar. For GVirtuS is basically the same. We have just to enable or not the OpenCL plugin. And the next thing is you can share the same physical device on different backend, different front ends, even using different virtualization libraries, for example, CUDA and OpenCL at the same time. One short word about the communicator. The communicator is a really critical component. The most part of the lack of performance in computation is due to the communicator. We have different communicators. The Unix socket is used just for testing purpose. It's used to check if the virtualization works, not to check real virtualization for because the limitation of Unix sockets. The TCP communication is mainly the most used in the most part of installations of GVirtuS because there are some. It was born for testing purposes. It was born to test the communicator, but then it was used for remote and distributed virtualization in cloud, and even in the high-performance Internet of Things, because in this way we can invoke GVirtuS or better CUDA kernels using GVirtuS even by a Raspberry Pi. There are other libraries with a really high performance in communication. For example, XenLoop. XenLoop is used for Xen. It is an interface between physical machine and a virtual machine, a high performance interface based on shared memory. And VMCI is exactly the same for VMware. And finally, in VM channel is used by KVM. That means it depends by which kind of application of GVirtuS I want to run, which kind of GPGPU as a service I want to set up, and I have to choose the communicator. But how it works, we know. How much it works, I will show you now. Basically, these benchmarks have been used, have been done with different configuration. This first one is about a cluster made by three TK1 ARM-based computing nodes that have on board their own CUDA device, but it's a really simple CUDA device. And but this cluster is accelerated by two NVIDIA Titan device on an x86-64 machine. On the left of the slide, the architecture of the cluster. On the right, in the center, the computation approach of MPI and CUDA matrix multiplication. This is a really common pattern in high performance computing and high performance cloud computing. So it's a benchmark that could validate the implementation. And we have the same test with one computing node, two computing nodes, and three computing nodes, using GVirtuS and not using GVirtuS. When we use GVirtuS, when we don't use GVirtuS, we use the local CUDA device. When we use GVirtuS, we use the remote CUDA device. As you can see, the improvement of performance is remarkable. Now, let's consider another scenario. This is not a test. This is a real application. This is a real application about interpolation of geographical data. We use an IDVU algorithm. This is actually a really important application for GIS, weather, climate, geology, and with the basically with the availability of big data in earth science, the most part of model coupling is a problem of interpolation of really big data. And doing this with GPU is the only way to manage this, otherwise the computing time is really impracticable. And we use this benchmark of interpolation in many configurations. This first configuration is using two local machines. One is called Saturn, where we have a couple of GTX Titan X NVIDIA device. And on Saturn is set the backend, then a dedicated 1 gigabit Ethernet, and then another machine called Storm. Storm actually is this machine where GVirtuS was born. Storm is provided by a couple of NVIDIA Tesla 1060 CUDA device, basically too old to be used for the today requirements. Basically, even the software is not able to work, or is able to work with a really poor performance. As you can see, we can we have the on the horizontal axis we have the number of known points in interpolation, while on the vertical axis the computing time. The scale, of course, is not linear. As you can see, in using remote GPU, we have a really important improvement in scalability. Basically, we increase the number of known points, and we have a really poor increment of the time needed to computation. Let's consider another setup. In this case, we use Amazon Cloud. We use Amazon Cloud setup. We use Saturn as backend. That means the physical GPU is outside the cloud. And while we want to use free micro instance of Amazon Web Service virtual machine with, of course, no GPU to do GPU computing. And that's incredible. It works, first of all, and even the results are very good. Even considering the need to remote the computation from from Amazon Web Services to our physical machine in a lab. Now we consider cloud to cloud. This is a really interesting setup because we have the backend on an Amazon Web Service machine and the front end on the Amazon Web Service machine in the same zone, of course. And even in this case, the improvement in computation is remarkable. Now we have another setup. In this case, we have on the same on Saturn, on the same physical machine, one KVM virtual machine, and we execute the same test. Even in this case, we have a good improvement. Then we have two virtual machines. Of course, the performance with the two virtual machines are decreased, but in any case, still more convenient than not using computation as a service. GPU computation as a service. Now, in the introduction, I mentioned there is a mobile cloud computing application about GPU virtualization and above all GPU computing as a service. Just analyzing the Android architecture, we can understand why Android was so successful. Basically, there is a completely decoupling between the underlying Linux kernel and libraries like the WebKit, Media Framework, SSL are not reported here, for example, SQLite, whatever, and the application framework and the application that are written mainly in Java. The magic is done, or better, in this case, was done by the, or better, is done by the Android the runtime with the different version of the Android runtime. The just-in-time compiling was substituted by compiling at the installation, but basically the approach is exactly the same. This is very good because the abstraction, but there is a lack of performance, of course. We cannot compare an iOS-based application and an Android application on the same hardware, But the Android application to work even better needs more hardware resources. Is CUDA used in Android? Yeah, actually, with the idea of the Android is down level of features. Of course, all Android devices support CUDA, or only few Android devices support CUDA, or better, or no one Android device support CUDA. And actually, the NVIDIA Shield tablet and console game console use Android and CUDA. They have their own implementation. Of course, this is done adding a CUDA library in the library section, and it works on proprietary hardware, and of course, it's open source. So theoretically, it's not possible to execute CUDA kernels in Android. Nevertheless, yes. Basically, just extending the split driver model I already showed you. There is a component called GVirtuS for Java that actually is GVirtuS for Android. It's Java independent. It works even with Kotlin. And basically, the idea is, in this case, we have a different, we have a framework based on JNI that basically imitates the behavior of the regular front-end Linux. In this way, we have exactly the same backend for both Linux, theoretically Windows, and even Android applications. The architecture is almost the same. In this case, we have to manage the device code in the right way. We have to store kernels in Android. This is possible using binary large object, and then we can move the compiled CUDA kernel, or the fully compiled or partially compiled CUDA kernel on the Android application. In this case, once the Android application is enabled for cloud for GPU computation on the cloud, the use of GPU computation on the cloud is completely transparent. And even for this is really good for the developer, because if you have some let's say machine learning task, and you have you need for GPGPU computing for this task. If you want to deploy an application, a mobile application, you have to deploy the mobile application, the remote API, and a server backend with the GPU. While in this case, you have not to deal about the server backend, you have just to deal and focus on your application. You have to test your kernels, your x86, 64 physical machine, and then deploy the CUDA kernel on the mobile application. Is it running or not? Because the point is, it works or not, and if it works, how it works. Of course, it works. This is an application that was made exactly to test this in Android, and this application was used on different Android device in order to show that it's completely transparent for Android. We have the usual approach to test GVirtuS behavior using the matrix multiplication. In this case, is really similar to the one used in the first benchmark, but of course doesn't use MPI. This is the code, the original code on the left, the original code of matrix multiply in C from the NVIDIA SDK. And on the right is exactly the same code, but using the Java SDK developed for GVirtuS. In this case, the virtualization, of course, is not transparent. In this case, you have to use a
programming models to use the GPU on Android device. And this is what happens. You are running this application on different device. Usually in green, there's the results using GPU virtualization, and in blue, the results in using not using the virtualization. On the we test on a tablet using a ZenPad 8 with a Qualcomm CPU. We used on Pine 64, is really similar to a Raspberry Pi, just with more computing power. Actually, this is related to Raspberry Pi up to the number 3, not the number 4. We have to test with the number 4. And then the same with other machine. Maybe the most interesting is the Udunio. It's a really small ARM and Arduino device, and it's interesting because it's possible to implement. It's the demonstration that this works in Internet of Things environment. In this slide, actual results. It's incredible because in this slide we show the results of computation even using just the regular connection. There is not one improvement or whatever. Of course, for problem of small sites, the local computation wins. This happens, but when the computation is more demanding, the option of demanding offloading the code on the cloud, it's winning. This slide shows the results with 3G connectivity. And if I remember, these results were made using 3G connectivity while I was in Salt Lake City and the server was at the University of Napoli Bartella.
During the Rapid H 2020 project, we had the chance to cooperate with people developing the ThinkCare. ThinkCare is a wonderful piece of software that enables Android application, even Java application, to offload part of the CPU code remotely, for example, in a scenario of edge computing, and in order to gain performance. And so we tried to, and this is done using Android virtual machines running on the cloud. So we tried to merge the two offloading software in order to test a full CPU and GPU offloading scenario, and the one shown in this slide are the results. As you can see, for a small amount of computation load, of course, is the local computation is preferred, but as the computing load increases, the offloading option is the best one. Now it's the time for the conclusions. First of all, we have not to talk, when we talk about GPGPU as a service, we have not to talk just about the virtualization of GPGPUs, but about remoting. And actually, we answered in this presentation the question why GPGPU remoting. We have to how we answer this question, actually focusing on low power embedded device. Basically, the idea of using this kind of services is to accelerate tiny hardware that could exploit the accelerators that are proximal to the networking device. And of course, if a device has its own GPGPU, different tasks could be split between local and remote GPU application. For example, in the H2020 Rapid project, we had a test bed biosurveillance application by Herta that was based exactly on this paradigm. Then we have the scenario made by mobile devices, because in this way we enable the developers of mobile device application to use GPGPU programming. Actually, again, this is not a web service based idea. We don't, in using GVirtuS, we don't have to create a web service, maintain the web service, and making interacting the web service with the actual GPU performing the composition. No? In this case, everything is much easier because the developer have to develop its own her or his own code on the developing machine, maybe ARM64 desktop or an Intel 64 machine, performing all the testing, and then finally embed the kernels in the mobile device. Maybe a question could be, this works on Android. It could be possible making it working even on iOS devices. Technically, it's not impossible. The only limitation could be some policy that could be applied in the by the vendor, but this should be proven. We never tried this. Is the proposal that receive good for all season? No, definitely not. Some apps could be great if remoted with GPUs, and otherwise not. And as already told, with mobile devices we don't have to set up a web service, but we have to just embed a kernel in the mobile application. Finally, this is very last slide. GVirtuS is continuously updated. This is the GitHub URL. Now we are working on CUDA 11. Actually, each time a new release of CUDA is released, it's almost tricky be updated, because the most part of the work is, I have to say, reverse engineering or mild reverse engineering. But usually the most part of the function of the libraries are correctly ported. We have under development a new generation of communicators based on InfiniBand, VM channel, virtual I/O, and finally we have still to port some CUDA ancillary libraries to be completely compliant with the TensorFlow, because our target is enable the machine learning task provided by TensorFlow using GVirtuS. In the last part of the slide, there are some references. The citations, of course, are appreciated because are the golden point of this realm. For any question, my email is at the beginning of this presentation, and you can send email and freely perform your questions, both technical or strategical, about the GVirtuS experience in GPGPU as a service.